Okay, in this video, I'm going to discuss the idea of a critical number. This is a continuation of our discussion of the maximum and minimum values. According to the definition, a critical number of a function f is that number c belonging to the domain of the function such that either the derivative of your f at c is equal to 0 or the derivative of your f at c does not exist. So in other words, the critical number of a function, of course, when your derivative of your function at that number is 0 or the derivative of your function at that number does not exist. Let me illustrate this idea considering our example here. A function given by f of x equals 3x to the fourth minus 16x cubed plus 18x squared. Okay, so according to our definition, you have a critical number c whenever the derivative of the function at c is equal to 0 or the derivative of that function at c does not exist. Now, since this is a polynomial, we do not have the case where the derivative of the function does not exist because a polynomial function is defined for all values of x. That means that to find for the critical number, we only utilize this condition here, that the derivative of your function at c is equal to 0. So the objective is to find for that c, which is our critical number. Okay. Now you can have actually more than one critical number, right? And it's also possible that a function does not have a critical number. Okay. So according to the definition, to find for the critical number, we need to find for the derivative of the function. And the derivative of your function here is 12x cubed, right? Minus 16 times 3 is, what is that? I think that's 48, okay? X squared plus 36x, okay? So that's the derivative. Now, it says that you have a critical number when you're at c when the derivative is equal to 0. So to find for the critical number, to find the critical number c, we equate, okay, we equate the derivative. So let f prime of x be equal to 0, okay? And that means that you will have 12x cubed minus 48x squared plus 36x is equal to 0. So the objective here is to find for those values of x that makes the derivative equal to 0, or to find for x that satisfies this equation. And to do that, we can first factor out the common, which is 12x, right? And then we have x squared minus, I think this is 4, okay, x, then plus 3, right? Equal to 0, or factoring, continuing with factoring, you have 12x. This can be factored here as x minus 3 and x minus 1, okay? So those are the factors. And using property from algebra, we can equate each factor by 0 because the whole expression is 0, right? X minus 3 is equal to 0, or x minus 1 is equal to 0. Okay, and you actually have here simple equations. You can easily obtain the value of x, no, from these equations. So that means that you have here x equal to 0 upon dividing everything by 0, by 12. This one here you have 3, right? And this one here you have positive 1, right? Okay, so these are your critical numbers for f. So critical numbers, okay, of f are 0, 1, and 3. So in this case, you have 3 critical numbers. Now, if you look at the graph, those values now that corresponds to these 3 critical numbers are, you will notice, okay, you will notice here that they correspond actually to local maximum or local minimum, or one of them is actually the absolute maximum or absolute minimum. The reason for that is, according to this remark here, if it says that if f has a local maximum or minimum at C, well, the absolute minimum here can also be considered as local minimum, right? Okay, so if your function has a local maximum or minimum at C, then C is a critical number of f. So you have here critical numbers of f, then which are 0, 1, and 3. Then there is a possibility that this 0, 1, and 3, in these numbers 0, 1, and 3, you have the local maximum or minimum minimum value, no, of your f. But the converse of this is not true, of course, no. It doesn't mean that the critical numbers would, if you have a critical number, it doesn't mean that it would correspond to local maximum or minimum. But according to this remark, if you have a local maximum or minimum, which is given here in the graph, then those values, no, that corresponds to the local minimum and maximum are your critical numbers. Okay, but of course, the critical numbers does not always correspond to the local minimum and local maximum, because there is also that case in the definition where you have a critical number when the derivative of your function does not exist. Okay, and I think that will be illustrated here in the next example, where the function given here is f of x equals x raised to 3/5 times 4 minus x. Okay, if you look at the graph, no, corresponding this one, look at this. You have obviously here a local maximum, or you can also call that as absolute maximum, of course, right? Okay, so if you check very carefully, it appears to be here equivalent to 1.5 or 3/2. Now we can confirm, we will check if indeed one of the critical numbers is 1/5. As far as the graph is concerned, that's the only value, no, that corresponds to the critical number. But let's see. Okay, what if we compute this algebraically or analytically? Do we find only one critical number, or can we find other critical numbers aside from 1.5? And of course, the question is it really, is one of the critical number really equal to 1.5? Well, according to the remark a while ago, we are told that if you have a local maximum or minimum, you are sure to have a critical number. And because this is a local maximum, okay, then you must have a critical number there. But we're not yet sure if this is really 1.5, no? Maybe this is 1.4 something, but let's check, okay? So according to the definition for a critical number, we first compute for the derivative of the function. And the function is given by x raised to 3 over 5 times 4 minus x. Computing for the derivative of this can be done by product rule, or you can also choose to distribute first, multiply this x to the 3 over 5 to 4 minus x, then proceed to finding the derivative. I think I will do it the hard way, and that means we're going to use the product rule. So according to the product rule, you have the first times the derivative of the second. Now the derivative of the second is -1, right? Then plus the second times the derivative of the first. Now the derivative of the first is 3 over 5 x raised to -2 over 5, okay? And then we can write this as negative x raised to 3 over 5 plus 3 over 5. Actually, we can write this as 3 times 4 minus x over 5 x raised to 2 over 5, right? Okay. And let's combine this as a single fraction, taking 5x raised to 2 over 5 as your common denominator. Then that would mean, since this the denominator of this is equal to 1, then that would mean that this will become x 5 now, 5x raised to x raised to 2 over 5 times x raised to 3 over 5. So that will be x raised to 3 over 5 plus 2 over 5, which is equal to 1, right? Then plus, you have here 3 times 4 minus x, or yeah, 3 times 4 minus x, okay? And simplifying further, you have, of course, 3 times 4 here is 12. The negative 5x and negative 3x, that will become negative 8x, okay, over 5x raised to 2 over 5. Okay, so this is the derivative. Now, to find for a critical number, there are two possibilities, no? One is your derivative is 0, or your derivative does not exist at C. Here, you can obviously find the critical number based on the idea that the derivative does not exist at x equal to 0, right? Because if x is equal to 0, then this is undefined, right? So therefore, the derivative does not exist at x equal to 0. So we have here f prime. So we say, since f prime of x does not exist at x is equal to 0, because when x is equal to 0, that will make your derivative undefined. Then this means that 0 is a critical number. Okay, 0 is a critical number. Now, to find other critical numbers, to find the other critical number, no? We already have one critical number, okay? Other critical number, we let your f prime of x equal to 0. That means that you will have the derivative of your f, no, which is 12 minus 8x over 5x raised to 2 over 5 to be equal to 0. So solving this, we need to get rid of the denominator by multiplying both sides by 5x raised to 2 over 5. So you are left with 12 minus 8x equal to 0, right? And solving for x, you will have x equal to negative 12 over negative 8, which is equal to, what is negative 12 over negative 8? That's equal to, so let's just write 12 over 8, but 12 over 8 will give you 3 halves, right? Will give you 3 halves or 1.5. So the critical numbers are numbers of f are dalawa, no? The first one is 0, and we obtained that 0 using the condition that the derivative does not exist, okay? And the second one is 3 halves, okay? So these are your critical numbers. Now for 3 halves, it's not surprising because according to the remark, you have a local maximum here. So naturally you have a critical number corresponding that. And indeed that's equal to 1.5 or 3 halves. But for 0, why is 0 considered as critical number? Well, the reason for that is your function, I mean the tangent line, no, corresponding that particular point. Kasi if you consider the tangent line, no, as the tangent line as you approach 0 from the right and from the left, the tangent line tends to be vertical, di ba? Now, you remember during our discussion about cases, no, where the derivative does not exist. One is when you have a corner or kink in the graph. The second is when you are at the point of discontinuity. At the point of discontinuity, there is no derivative there. And the third one is when your tangent line is vertical. Kasi if you have a line that is vertical, the derivative of that is undefined. So that's the reason why 0 is considered to be a critical number. And this is also an example of the case that the converse of this remark is not always true. No? Now, even though you have a critical number, okay, of f there at that point, it doesn't mean that you have a local maximum or minimum. But if you have a local maximum or minimum, you are sure to have a critical number there, right? Okay. So this is for the critical numbers.